The second half of the equilibrium unit talks about acids and bases, because in a weak acid and a weak base combination, they exist in equilibrium as well. Either when they're reacting with each other or just when they're sitting in solution with water, they exist in equilibrium. So the Chem 20 that you learned about with acids and bases, they all existed as 100% stoichiometry, strong acid, strong base. So here we're going to be looking at weak acids like vinegar and how they exist in equilibrium. So some Chem 20 stuff that you need to know are things like the Chem 20 formulas. You'll have to have those memorized. Understanding that the pH scale and the pOH scale are opposite of each other, 1 to 14, all that kind of stuff. So that's in your notes package, all of that review packet, all that review stuff, but that's Chem 20, and you do have to know all of that. If I ask you for an empirical definition of an acid, you're looking for lab stuff. Turns red litmus paper blue, for example, right? Or tastes sour. So any empirical definition is what you would see in a lab. That's like your junior high definitions. Then Arrhenius is like your science 10 definitions. So acids have an H+, bases have an OH-. For example, an acid is HCl and a base is NaOH. Okay, then we get into the modified acid-base theory, or the Bronsted-Lowry acid-base theory. So Arrhenius was like great. He came up with this theory that all acids have H+, all bases have OH-, and he said, but there's some exceptions. Like, for example, NH3 acts like a base, but you might even predict that it was an acid, but it's definitely a base. And so Arrhenius had all these, he understood there were exceptions, but he said, I've done a lot of work. I've come up with some good stuff. My name's going to go in the textbook. Don't really care after this. So here are the exceptions, and some other scientists can sort that out. So Bronsted and Lowry, two scientists working in two different labs at the same time, came up with the understanding that they looked at all these exceptions and they said, you know what, we're going to change the definition of an acid to not just be that it has an H+, but rather that it donates an H+. And what an H+ really is a proton. So now when I say proton donor, you have to think proton, H+, and H3O+. It's all the same thing. And a base is a proton acceptor, so it's going to take an H+, an H3O+, etc. And then another new word is a conjugate. So conjugate acid or conjugate base are going to be the products. Okay, so let's see some examples of this. So here, if I'm reacting some HF, which Arrhenius would say was an acid, right, because it has an H in it, or NH3, now this is an ambiguous one. Empirically, it presents itself like a base. It turns red litmus paper blue, but one would even predict that it has H's in it, so it should be an acid. So with Bronsted and Lowry, they can say, oh, but I bet you, because it empirically acts like a base, it'll be a proton acceptor. So here's my acid, here's my base. This can donate a proton there. This can accept a proton. So by definition, this is a Bronsted-Lowry acid. This is a Bronsted-Lowry base by definition. Okay, because this is donating a proton, this is accepting a proton. By proton, I mean H+. So when this donates the H+, right, when this guy goes over here, he becomes NH4+ instead of NH3. So we've added an H+ to his system. And this becomes F-. He lost the H+. So now the Bronsted-Lowry base becomes the conjugate acid. It's always the opposite. And the Bronsted-Lowry acid becomes the conjugate base. So they're a pair. So the HF lost its H and became F. So it's the pair, the conjugate base. Now the reason they're called these, the opposite, if it was an acid, it's now a base. If it was a base, it's now an acid, is because of the equilibrium arrows. This acts like an acid in the reverse direction. This acts like a base in the reverse direction. Because remember, this is still at equilibrium. The forward reaction, the rate of the forward equals the rate of the reverse. Everything's happening at the same time. And so actually in this reverse reaction, you see that H plus going back onto that F as it goes this way and forms the HF and forms the NH3 back again. So this is acting like a proton donor, which is the conjugate acid. This is acting like a proton base. So therefore it's the conjugate base because it's written as the product. Okay. Here we have another example. If I have some of this acid just in water, how does it exist in equilibrium? So this is a molecular compound. Technically, these are not free. They are free H pluses, right? They are held together in a covalent bond, a shared pair of electrons. So in order for it to show evidence of an acid, it must exist in this equilibrium. So here's my H's going onto my water. My waters have gained an H plus, right? H2 became H3, neutral became plus. So H plus, it gained. So this donated a proton, so it's a Bronsted-Lowry acid because by definition, Bronsted-Lowry acids donate protons. This accepted a proton, so it's a Bronsted-Lowry base. And it became, the water became the H3O plus, so it's a conjugate acid. And this became a conjugate base. And you can see in the opposite direction that would be donating a proton that way to go this way, and therefore it's an acid. And there's your pair, and there's your pair. Just a little note that like this can only donate a proton, it can never accept it. This could only donate a proton, it can never accept it. This could only give away a proton, it couldn't accept another one and become NH5 2 plus, right? But some are called amphiprotic. So water could either accept a proton and become this, or it can donate a proton and become OH minus. So H2O could become H3O plus by gaining a proton, or it could lose a proton and become OH minus. So some of these things are amphiprotic. I'll give you another one that's amphiprotic. HSO4 minus. So HSO4 minus could become, in fact, you know what, let me write it in here. HSO4 minus could become H2SO4 if I pop on an H plus. So the plus and minus neutralized each other and became that. Or it could give away an H plus and then it would become SO4 2 minus. So here's just playing around with donating protons and accepting protons in terms of a Bronsted-Lowry acid or a Bronsted-Lowry base.